Okay, that's what I wanted to do. All right, so I think we're good now. Okay, so we're continuing on with 11.10. We only have two sections left, 11.10 and 11.11. Some reminders. So quiz on Friday, our last regular quiz. Exam is on Thursday the 9th. Okay, that means Friday the 10th would just be a glorified office hour. Final exam is the 17th. The final week begins on the 13th. We don't meet on Monday, Tuesday, Wednesday, Thursday. If you have other final exams with your other instructors, go to them, of course. But our final is on Friday the 17th, 8:10 to 10:40. Okay. And to study off the old exams. And these are my office hours during finals week, Tuesday, Wednesday, Thursday, 8:10 to 10 a.m. The same Zoom link as usual. Okay. Okay, so continuing on with section 11.10. And let's just review what you need for your formula sheet, your cheat sheet. By the way, for the final exam, you can have 5 cheat sheets, one for each exam. And again, the easiest thing to do is just bring the old cheat sheets if you didn't throw them away. Just bring them in. You can add to them also. So page 760, you want to have box 6 for the Taylor series, box 7 for the Maclaurin series. I haven't done too many Taylor series yet, but I will. Here's the Maclaurin series. Okay, Taylor's inequality, page 762. We won't get to this until actually section 11. Okay, but you can have it. I'm going to modify it. Okay, the way I'm going to modify it is I'm going to put this thing right here. If you put this thing right here, it says fn plus 1 of x, x minus a to the n plus 1 over n plus 1 factorial. That kind of looks like stuff we've already been doing. It's the n plus first derivative exponent and factorial. Okay, that's the way I'll be presenting it. And the Big E table on page 768. Okay, so this one, formulas for e to the x, sine x, cosine x, inverse tangent of x. Okay, and don't worry about these. In case you're wondering what about the other trig functions, they're there, they're not as easy. Okay, but frankly, they're kind of difficult. So let's say on a calculator, if you want the calculator to do tangent, it would just take that answer and divide it by that answer. That's probably the easiest thing to do. Okay. All right, and remember our ground rules or my ground rules is write out at least 4 terms of these infinite series, okay, for the final answer. Okay, so let's pick up where we were. By the way, quick reminder, have polar graph paper for the final exam. I'm not promising I will, but have polar graph paper in case I ask you a polar graph problem on the final exam. Okay. Okay, here's problem 47. F of x equals x e to the negative x, write the Maclaurin series. So start off with e to the x. E to the x is x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial. Yes, that's the same as 1. Yes, it's the same as x, but to me, this is easier to memorize. Yeah, I realize you don't have to memorize, but you know, if you were to do that, that's what you would do. Okay, then just like any other function, e to the negative x, change that to negative x. So negative x to the 0 over 0 factorial, negative x to the 1 over 1 factorial, and so on. Okay, then I clean that up. That's still 1. This is minus x plus 1/2 x squared minus 1/6 x cubed. Okay. And you should be somewhat familiar with the easier factorials. So 0 factorial is 1 by definition. 1 factorial is 1 by definition. 2 factorial is 2, 1 times 2. 3 factorial is 3, 1 times 2 times. 3 factorial is 6, 1 times 2 times 3. Okay, 4 factorial is 24, and so on. Okay, I can maybe just for fun, I'll show you the first few factorials. But anyway, just to finish this problem, then just multiply both sides by x. So x e to negative x, multiply that by x, you get x minus x squared plus 1/2 x cubed minus 1/6 x to the 4th plus dot, dot, dot. So here's a power series expansion Maclaurin series for x e to negative x. Okay, and in some circumstances, which would you rather work with, that or that? right? Like if we were to take a derivative, product group. If you were to integrate by parts. But look at this, that's easy to, polynomials are easy to differentiate, very easy to integrate, if you're willing to put up with this infinite polynomial stuff. Okay. And yeah, I will digress a little. I think it should be, you should be somewhat comfortable with the earlier factorial. So 0 factorial is 1. 1 factorial is also 1. 2 factorial is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 24. Okay, so I think you definitely should memorize these, but even if you don't memorize it, it doesn't take that much time to go 1 times 2 times 3 times 4, if you know what they mean. Okay, I've gone up to 6. So anyway, 5 factorial is 120. 6 factorial is 720. And that's as much as I'm willing to go. But anyway, those are some of the factorials. Okay, so now I'm going to do some Taylor series where you're not centered at 0, you're centered somewhere else. Okay. So 5, 7, 9, they give you an A, that tells you where you're centered at. Okay. Okay, first one I'm going to do is actually not from our text, it's 13 star. It was from the previous edition. F of x equals x to the fourth minus 3x squared plus 1, centered at a equals 1. Okay, so we're centered at a equals 1. So that's the case where I'm doing this one for the first time. Page, if I can get this thing focused, page 760, box 6, centered at a. So it's x minus a everywhere. And instead of plugging in 0 for all the derivatives, I plug in a. All right, so here's the function, f prime for x cubed minus 6x. Double prime, 12x squared minus 6. Triple prime, 24x. F4 quadruple prime. Once you get past 3, just write the number. F4 is 24. And then all the derivatives after that are 0 for n greater than or equal to 5, right? The fifth derivative is 0, so is the sixth, so are the rest. Okay. And then instead of plugging in 0, I plug in 1. So 1 minus 3 plus 1 is negative 1. Put a 1 here, 4 minus 6 is negative 2. Put a 1 here, 12 minus 6 is 6. Put a 1 here, 24, 24, and that's it. Okay. So the formula for Taylor series, f of x, is summation n equals 0 to infinity of fn of a, the nth derivative, and the 0th derivative is defined to be the function itself, x minus a to the n over n factorial. Again, you should be happy that I'm not making you memorize this, because the last time I taught the class, I made everybody memorize it. The memory trick was DEF, derivative exponent factorial, because we all know the alphabet. Okay, so it's going to be x minus 1 to the 0 over 0 factorial. Yes, that's 1. Yes, that's 1. But to me, in terms of memorizing, once you have that, you got the rest. X minus 1 to the 1 over 1 factorial, x minus 1 squared over 2 factorial, x minus 1 cubed over 3 factorial, x minus 1 to the 4th over 4 factorial. And I don't need plus dot, dot, dot in this particular case, because in this particular case, the rest are all 0. And then the d's. So negative 1, negative 2, 6, 24, and 24. And I just clean it up. That's negative 1. That's negative 2 times x minus 1. 6 divided by 2 is 3, x minus 1 squared. 24 divided by 6 is 4, x minus 1 cubed. 4 factorial is 24. 24 divided by 24. So x minus 1 to the 4th. All right, so here is the Taylor series of the original polynomial centered at x equals 1. Okay, so the problem's finished, but a side note, this is not an infinite polynomial. It is a polynomial. So what we're doing is giving polynomial approximations to functions. What's the best polynomial approximation for a 4th degree polynomial? Well, it's the polynomial itself. Okay, so we won't bother to take the time for it. But if you were to actually multiply all of this mess out, you should get that back. because what's the best approximation for a polynomial? It's already a polynomial. Okay, so what about all of our other functions like sine, cosine, e to the x? Those are approximated by infinite polynomials. Okay. So anyway. Okay, f of x equals natural log of x at a equals 2. And let's see, can't even read my own writing there. That used to be 15, or is this a starred one? No, the next, it's 21. Yeah. Okay. So it's 21. I guess it was 15 in the previous edition. Okay, so find the power series expansion about a equals 2. And by the way, you might say, why don't we always center it at a equals 0? Well, for natural log, you cannot. You're not even allowed to plug in 0, right? So this one's going to go infinitely far. So we'll do the Melvin-Hom rule of having at least 4 terms in my answer, which means it's generally going to be a cubic, unless some of the terms are 0 and then dot, dot, dot after that. Okay, so I take 3 derivatives. F0 means the function itself. First derivative is 1 over x, which is the same as x and negative 1. Second derivative is negative x and negative 2. This is better for calculus. This is better for algebra. Negative 1 over x squared. And f triple prime is 2x and negative third, or 2 over x cubed. Now I plug in 2 everywhere. ln 2, 1/2. Negative 1 over 2 squared is negative 1/4. 2 over 2 cubed, that's 2 over 8, 1/4. All right, so even before the problem starts, I think you can kind of see these coefficients that are in red. So even before we start, the e and the f, exponential and factorial. Okay, if I were teaching face-to-face the last time I taught it, I kept saying d, e, and f. That's my memory trick, derivative, exponent, factorial. In case you say, I'm never going to memorize this. And they did, derivative, exponent, factorial. Okay, right from the get-go, the e and the f are already predetermined. So once I see this with a equals 2, it's automatically x minus 2 to the 0 over 0 factorial. Yes, that's 1. Yes, that's 1. But to me, this is easy to memorize. Once you have that, just make them 1 and 2 and 3. X minus 2 to the 1 over 1 factorial. X minus 2 squared over 2 factorial. X minus 2 cubed over 3 factorial. So that's the e and the f, the exponent and the factorial. And then adding to the coefficients are the d's. I have them in red. Not sure if you can see that it's reddish here. Okay, so ln 2 goes there. Half goes there. Negative 1/4 goes there. Positive 1/4 goes there. And then I just clean it up. Okay, so that's natural log of 2. Half divided by 1 is a half. Usually these first 2 terms are pretty easy. Then it gets a little bit tougher by the time you get to this. So granted, the last one is usually the hardest. So we usually stop with that. That's usually our 4th term anyway. So we've done some easy ones and these are a little bit harder. Okay, so negative 1/4 divided by 2. Okay, you should know from algebra, this 4 gets to slide down with the 2. That makes it negative 1/8, x minus 2 squared. And then 4 slides down with the 6. 4 times 6 is 24. So 1 over 24, x minus 2 cubed. Okay, so here is the Taylor series of the natural log function centered at x equals 2. Okay, so if you want a good approximation of the natural log function near 2, you can plug into this. This is just a polynomial. Okay, so that's what we got. Okay, now, next one I'll show you is, well, I'm calling it 19 star. It's the cosine function. So the one that's closest to this one is number 9, sine function. So this is sort of like problem 9, cosine function. Now you might say, I already have a formula for cosine. That's right. That's the Maclaurin series centered at 0. So this table that I showed you, these are all Maclaurin series centered at 0. That's our favorite. We don't have to center at 0. We could center somewhere else. In particular, we could center at pi. We could center anywhere they feel like. Okay, so the function is cosine. F prime is negative sine x. F double prime is negative cosine x. And F triple prime is back to sine x. Now, plug in pi. Cosine of pi is -1. Negative sine of pi is 0. Negative cosine pi, that's -1. 1. And sine of pi is 0. Okay, from the get-go, once they tell me we're centered at pi, automatically the E and the F are determined. It's going to be x minus pi to the 0 over 0 factorial. Yes, that's 1. Yes, that's 1. X minus pi to the 1 over 1 factorial. Yes, that's 1. X minus pi squared over 2 factorial. X minus pi cubed over 3 factorial. And then going in as coefficients, -1, 0, which means that's gone. 1, 0, which means that's gone. So I just have -1 times x minus pi to the 0, that's 1. 0 factorial, that's 1. So -1 plus 1/2 x minus pi squared over 2 factorial, which is a half. Okay, but that violates the Melvin-Hahn rule of having 4 terms. But you can go by the pattern, right? It'll just keep going -1, 0, 1, 0. Okay, so the next one will be the third D, E, and F, the third degree x1 factorial will be gone. This one will be x minus pi to the 4th. The 5th would be gone, and the 6th would be there. Okay. And I just make it alternate. That seems to be the pattern. So 1 over 4 factorial, 24, plus 1 over 720, 6 factorial, x minus pi to the 6th. So here is the Taylor series for the cosine function centered at pi. Okay. What that actually means is that if you want to get an approximation for cosine of a number close to pi, this would do a better job than the Maclaurin series centered at 0. Okay, I mean, it would still work. You just have to go farther and farther and farther out. This does a better job near pi. Okay. All right, next one I want to show you is, I guess it's 43. Double checking the text. Yes, this is 43. It used to be 37. So sine squared x, and they tell you to make it into 1 minus cosine 2x over 2. All right, so just like a function, I'll start off with cosine x, which is x to the 0 over 0 factorial minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And why do I put this one here? I thought you said only 4 terms. Yes, but I realized this is equal to what? That's 1. I'm going to subtract off that 1, which means I only have 3 terms. That's why I need 5 terms at the beginning for this one. Okay, so I start up with 5 terms. Okay, then cosine of 2x. Put 2x here, 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 and here. That's still going to be 1. Minus 2x squared over 2 factorial. 2x to the 4th over 4 factorial. 2x to the 6th over 6 factorial. 2x to the 8th over 8 factorial. Okay. Then I'm going to go 1 minus all of that. Okay. If I go 1 minus parentheses, 1 minus, that's going to be gone. All of these will change sign. Is that right? 1 minus cosine 2x. It's 1 minus all of that. 1 minus parentheses, 1, all that. So 1 minus 1 is 0. That's gone. And all of these will change signs. Okay, so now we have the 4 terms that I require for my final answer. So that's why I wrote 5 terms here. I wrote 5 terms because I realized this was 1. I'm going to lose the 1 when I do the subtraction. Okay, so that's now positive, negative, positive, negative. And then I just divide everything by 2. Divide both sides by 2. And I have it. So sine squared x, 1 minus cosine 2x over 2. Okay, I'll let you clean up the arithmetic. But this is going to be, okay, let's see. 4x squared divided by 2 times 2. So it's just x squared. Minus, okay, 2 to the 4th divided by 2 is 2 cubed. X to the 4th over 4 factorial. 2 to the 6th divided by 2 is 2 to the 5th. X to the 6th over 6 factorial. Minus 2 to the 8th divided by 2 is 2 to the 7th. X to the 8th over 8 factorial plus dot, dot, dot. And just clean up the arithmetic. Okay, so that'll be the answer. Okay, maybe I'll help you with the easy one. X squared. That's going to be what? 8 over 24. So 1/3. And I don't feel like doing the rest. You do it. In other words, you shouldn't stop here. Just clean up the arithmetic. But, you know, you can all do arithmetic. That's what? 32 divided by 720. Just reduce the fraction and reduce that fraction also. Okay. All right, now 49. Use the Maclaurin series for cosine x to compute cosine of 5 degrees to 5 decimal places. Cosine of 5 degrees. 5 decimal places means 0.00001 or 10 to the negative 5. Okay, and as we mentioned earlier, for a cosine of 5 degrees, calculators actually prefer radians. Okay. So on your calculator, if you get your mode thing, right? Even if you switch it to degree mode, when the calculator does it, it says, no, I don't want degrees, I want radians. So it switches automatically inside. I mean, you don't see that yourself. Again, you and I are probably more comfortable with 37 degrees, 53 degrees, 323 degrees, right? We don't like this radians, okay? But when you give a calculator something like cosine of 47 degrees, the calculator, as a word says, no, I don't want degrees, I'm going to switch it to radians and then work it out according to the formula, okay? So all of these formulas for cosine, sine, inverse, tangent, they're meant to be in radians. Where was I? So the first thing we need to do is change this to radians. So you know the conversion factor, 5 degrees, pi radians divided by 180 degrees. Yeah, this is problem 49. It was 43 in the previous edition. So pi over 36 radians. All right, so cosine of x, x to the 0 over 0 factorial. Yes, that's 1. Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8th over 8 factorial. Okay. Plug in pi over 36. Awkward for you and me, but easy for calculators. 1 minus pi over 36 squared over 2 factorial plus pi over 36 to the 4th over 4 factorial, 24, minus pi over 36 to the 6th over 6 factorial, 720. Okay. This is an alternating series. Terms decrease in absolute value and approach 0. Therefore, the series converges by the alternating series test. And the alternating series estimation theorem says if we stop anywhere, the error is no more than the next term. Okay. I punched this out before. That's roughly 7 times 10 to the negative 10. This is like 3 times 10 to the negative 6. Okay. That's already good enough. Okay. Maybe I'll just try to show you that to you. So let me see if I can show that to you. Pi divided by 36 to the 4th power divided by 24. 2.41, smaller than 3 times 10 to the negative 6. So that's already within 5 decimal places, which means all you have to do is just add up 2 terms. So 1 minus pi over 36 squared over 2, 0.99619. So instead of adding up infinitely many terms. I only added 2 terms. You're still already good to 5 decimal places, which is the whole idea behind this stuff. Okay. All right, then let's see. Let me show you an integration. And then we won't go much farther. $55 cosine x minus 1 over x. By the way, this cannot be done by conventional means, but by power series, it's not too bad. So I write down the formula for cosine x again. And notice I put 5 terms down because I knew I was going to lose the 1. So x to the 0 over 0 factorial, that's 1, minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6 over 6 factorial, plus x to the 8th over 8 factorial, dot, 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 minus 1 all over x. That cancels out. Okay, and I'm dividing by x. So that becomes x, x cubed, x to the 5th, x to the 7th. Okay, so minus 1/2 plus 1 over 24 minus 1 over 720 plus 8 factorial is 40,320. So 1 over 40,320 x to the 7th. Okay, so indefinite integral means I put a c minus 1/2 x squared over 2 plus 1 over 24 x to the 4th over 4 minus 1 over 720 x to the 6 over 6 plus 1 over 40,320 x to the 8th over 8 plus dot, dot, dot. And that's about it. The last thing is to do the arithmetic. You could do arithmetic very well, but I won't take up class time for that. That's 1/4. That's 1 over 24 times 4 is 96. And, you know, clean up the rest of that. Okay. All right, I was only going to do one more, and then I'll stop. Let's see, it looks like 57 or 51. It's our 57. Yeah. Integral of x cubed arctan x from 0 to half, 4 decimal places. Okay, that is not an easy integral to do by conventional means. Just can't do it. But by doing series, it's not so bad. So arctan, formula for arctan, x to the 1 minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. You can find that on that page that I gave you, right? By the way, this is the same as sine, except the sine had factorials. This one didn't. Okay, then multiplied by x cubed arctan x. So that becomes x to the 4th minus 1/3 x to the 6th plus 1/5 x to the 8th minus 1/7 x to the 10th plus dot, dot, dot. Then you integrate both sides from 0 to half. X to the 5th over 5 minus 1/3 x to the 7th over 7 plus 1/5 x to the 9 over 9 minus 1/7 x to the 11th over 11 plus dot, dot, dot from 0 to 1/2. Even though there's infinitely many terms, what happens when you plug in 0? They're all 0. So I plug in a half. 1/2 to the 5th over 5 minus 1/2 to the 7th over 21 plus 1/2 to the 9th over 45 plus 1/2 to the 11th over 77. Okay. All right, and then we just want to within 0.0001 10 to the minus 4. Okay, and I think this one was already below. So again, this is alternating. Terms decrease in absolute value and approach 0. Therefore, the series converges by the alternating series test. If we stop anywhere, the error is no more than the next term. So we want accuracy to within 10 to the minus 4. I believe this is already it. So 1/2 or 0.5 to the 9th power divided by 45 is 4.4 times 10 to the negative 5. That's already smaller than 10 to the minus 4, 0.0001. So you just have to add up the first two terms. Okay, so if you added the first two terms, 0.0059. Okay. All right, and that's as much as I was going to do today. I'll stop there. Next time I'll do some more of these problems, but I'm getting close to the end of the section. And then we'll just take it from there. Okay, so let me stop the share. So is any questions, please? Otherwise, we're done for today. Anything in the chat? Nothing in the chat. Okay, any questions, please? All right, then that'll do it for today. All right, so have a good day, and we'll see you next time.
All right, take care, Professor.
All right, thank you. Bye, everybody.